it's really a great pleasure to be back, and it's really amazing to see all the progress which has been made over the years, and it's fantastic to be home again. And so there is quite a pretentious title, materials for the future, and I hope you will see what do I mean by this. But of course, the graphene is still a very, very convenient place to start talking about the future, because it's of course is the most simple material you can imagine, because it's only two-dimensional arrangement of carbon atoms. Carbon is one of the lightest elements, so what can be simpler, and yet it has all those similarities which we all love. So either in physics or in technology, the highest mobility for the carriers, the lightest, the most impermeable, flexible, and stretchable, and so on and so on and so on. And of course, all those unique properties gave rise to a number of different applications, from energy to composites, from electronics to sensors. And it's really interesting to see, even though for many of us who've been working with graphene for many years, it feels like a very, very special material. When it comes to applications, it's actually not that special at all, because it follows exactly the footsteps of all the previous advanced nanocarbons, like fullerenes or carbon fibers or carbon nanotubes. They all first start being applied in composite materials, usually in sport goods, for obvious reasons. I mean, we in probably even before GIG, right? So we were guilty to collaborate with Richard Miller and McLaren to create this world lightest, unfortunately also world most expensive watch, 1 million Swiss franc for 32 grams of watching. So it's definitely by far most expensive per gram. And okay, so but we can go to much cheaper products as well. And I'm really happy to see the new model of the BAC mono here. But then being serious, if you go to China now, the amount of the production of graphene, a lot of that goes, so by tonnage, by far the biggest consumer are the batteries. So batteries consume hundreds of tons, if not thousands of tons. But then the next one is thermal management, and I'm really surprised. And it's a unique material for thermal management. You get 1500 watt meter Kelvin from graphene. Copper is 400. So you get the flexibility, which is very important for the flexible phones, and you get the highest thermal conductivity. And honestly, the production is not that. I mean, it's still a process and it's still a technology, but it's not massively difficult. And we're really hoping to. And actually, many of our graduates work in that technology, and but now it's a commodity in China. There are so many factories who produce only the thermal management, either for the mobile phones, laptops, a lot of military applications there. So it's quite interesting to see this development. And I would say that probably the next development which we hope to see progressing fast is the applications in the optoelectronics. So you know that our internet traffic is all over the optical fiber, which is great. The problem is we don't know how to manipulate the optical signal. If you want to do anything with the optical signal, you have to convert it into electronic domain, do something with the signal, modulate it, multiplex it, and then convert back into the optics, into photons, and then send it further. So ideally, what would be nice if you could operate with the optical signal directly, but for that you need materials which can change their refractive index, their optical properties, according to the applied gate. That's of course all graphene, so combined with silicon photonics, and across the globe they're building a lot of the silicon photonic hubs. In Europe, they built one for silicon photonics in general, including graphene, and two specifically for graphene. So it's so each hub is about 300 million to 600 million investments from European Union. So 2.5 graphene hubs in Europe alone. So that's, and I really hope that it's going to change the way we do telecommunication. I should say that 2D materials, they actually they have another interesting property. So I will talk briefly about other 2D crystals, not only graphene, which is a semi-metal. There are a variety of the other one-atom thick fabrics. Some of them are semiconductors, and we can make quantum dots for quantum telecommunication, and it is also combinable with the silicon photonics. Anyway, so for some time there was there was a question, of course, if we can produce enough graphene, because for those who visited NGI yesterday, so those guys mainly do the old-fashioned Scotch tape is the quickest way how to produce high-quality graphene. So 1-2 minutes, and you get fairly large crystals of very, very high quality, pretty much zero defects in those. But of course, industrially, you need something else, and luckily these days we have a huge variety of different methods. Many of them are presented downstairs here. So the most popular for electronic domain is the chemical vapor deposition, where you run the carbon-containing gas on top of a hot catalytic surface, and so the methane or acetylene cracks on the catalyst. Hydrogen flies away, which is important by itself, and I'll tell you later why. And then carbon rearranges on the surface as a monolayer, and because it's a catalytic process, it's self-limited. You get exactly one layer of graphene. The beauty here is that you can use pretty much any carbon feedstock here. So some time ago we needed some iron-doped graphene for our Conda experiment. So we basically use this. So what you do, you just prick your finger, spread it on copper, stick it into the furnace, and then you get your iron-doped graphene. So it was originally meant as a joke, but then my students picked it up. So we actually even managed to publish this work after the editor had to take a word from me that it was that those were my fingers, not the students' fingers. But it actually, so even though meant as a joke, there is some rationale on it, because I'm sure that, and I see some companies working in the same area here. I'm sure you've seen pictures like this with the flares on top of many petrochemical plants, many refineries, and in those flares, in principle, they say that they shouldn't be if the process runs correctly. But so I live so in Singapore. I live opposite to Jurong Island, which is one of the largest refinery in the world, and you see those flares all the time. And we have to burn methane because it's much worse greenhouse gas than CO2. It's better to emit CO2 than methane. So. And in those flares, we have everything we need for graphene. We have the high temperature, we have the carbon-containing gas. So we produce those machines which don't need electricity. They take the heat and the carbon feedstock from the flares, and then you can convert it into graphene. Or so actually what guys are doing here is even better than in our case. So we still use the catalyst, but say for or probably equally good to produce carbon nanotubes, because you can do it in a more continuous process, and then you can. So there are two benefits here, because you can. We know exactly how much graphene we produce, so we have the so-called proof of work. So we register it directly on the ledger, on the blockchain. So we can claim our carbon credits straight away, so that we didn't throw this carbon into the atmosphere. And then, of course, the big hope is to link this to the another of the Manchester invention, to the concrete, and then you actually you get carbon from the atmosphere, but you also reduce it, the CO2 emission further by utilizing that carbon in your concrete. So it's a spiral economy. So it's really double effect here. Okay, so there are many other ways how to produce graphene. So depending on the particular application you use different methods here. And so the next step in the story was when some investments started to come to Manchester to build NGI and Geek, and we managed to spare some of the money, not to spend it on brick and mortar only, but to put a little bit into science. So we managed to buy not only the lead pencils, but also some other colored pencils, and then you can, if you exfoliate those, you can get some other two-dimensional crystals. So these days we are not only talking about graphene, we talk about a whole new family of materials. They're all one atom thick, or one unit cell thick, but then unlike graphene, which is a zero overlap semi-metal, there are many other properties which you can get with those new materials. So there are insulators, there are semiconductors, there are metals, superconductors, ferromagnets, ferroelectrics. So there are you name it. And it's of course, for a scientist, it's a paradise, because you can always find something interesting in this zoo of materials, and once you go to 2 dimensions, you get some interesting properties always. So it's really lovely to investigate all those crystals. But then the next step, which was really a lot pioneered by people in the NGI, was when we realized that actually what we have is a fantastic building block to create artificial materials on demand. When we can assemble those 2D crystals, so we have those monolayers in the lab, and we can start putting them together on top of each other to create artificial materials which never existed in nature, but we can do them in our laboratories. And these days, it's this one of our heterostructure engineering is probably one of the most fast developing front in condensed matter. And so many devices, many crystals have been created. You can make transistors this way, you can make resonant tunneling diodes, so you can make LEDs like here, you can make lasers out of it, photo detectors, everything. And the variations of the possible structures is really huge, because you can combine. So you got good couple of hundreds, 300 of those materials already which exist experimentally. There are a few thousands predicted, so you can combine them in different combinations, different number of layers, different sequence. What is even more interesting, that even the way how you stack them. So when you put those crystals together, you have a freedom of rotating them with respect to each other. And I hope you can see this mesmerizing pattern appearing. It's called the Moore pattern, and apparently electrons, they feel quantum mechanically this this pattern when they travel through the crystal, and then it's our way how to modify the electronic structure so we can fine-tune the electronic properties of those materials. So that was a demonstration by our colleagues from MIT, Herrera group, who show that if you take 2 layers of graphene and you rotate them simply by 1 degree, you can turn it into a superconductor. And now the engineering of the electronic properties, optical properties of those materials by twist control, which is an additional knob which we've got, is really a very, very popular direction. So just if you give me a second. So basically, that was more or less state of the art and a long introduction before the end of my talk. I guess the message here is that the state of the art of the material science these days is that we can create artificial materials, tailored materials on demand with atomic precision, and that's the state of the lab in the art in the lab, and I hope that eventually it will get into industry as well. Now the question is, I promised you a little bit of a glimpse into the future. So what can we expect? What do we want from the materials in the future? We now have got pretty much everything. We can do any materials with atomic precision. What else can we wish? So rather than asking everyone of you what do you want from the future materials and how do you want them to be, so let me show you how other people answered to the same question before. So this is I hope many of you recognize is the Terminator 2 movie. And for those who didn't watch it, so the movie was made in 1991, and the plot is that a robot from 2029 sent back to 1991 to kill Sarah Connor and her son. And the only reason I'm showing it to you is to show how people back in 91 thought our future materials would be. So there would be everything was made from liquid metal, self-adjustable, self-healing, so just changing shape, changing color, and everything. So we are in 2024, and fortunately I've got bad news for you that unless we do something radically different, we have absolutely no chance to fulfill the dreams of the directors of the Terminator 2 movie. And the problem is not really with the robotics. It's fundamentally our technology is top down. So we make components, and then we assemble those components into the system level, and the individual components are only passive, so the complexity and the functionality appears only on the system level. You take the one cogwheel from that clock, and then it stops working. You take one transistor away, one screw away from the robot, they stop operational. So if you think, however, the biological systems, they work on a completely different pretense, where the functionality is spread across all the possible levels. You take, so it's proteins, the membranes and the cells themselves. We can take a membrane from the cell, and we can utilize the ionic pumps which are sitting inside of the membrane by themselves. So it doesn't need to be inside of your body. It will still be operational. And that's the question which we want to answer. Can we create materials which has some functionality on their own rights, that when you assemble them into the system, they're actually functional components, they're not passive components? Just let me give you maybe an example of what I mean. Quite a lot of work in NGI and in GEEK are diverted towards the graphene membranes for desalination or for filtration. So it's a very important technology, very fast-moving technology. Say in Singapore, 99% of our water comes through a membrane, and not graphene. So, but in Australia, there are a number of companies which produce commercial graphene membranes for large organic molecules separation. Anyway, it doesn't matter which membrane do you use. You have to control the quality of the water stream there, right? So you put a sensor downstream, which would analyzes the quality of water, sends a signal to a computer. Computer makes a decision, sends a signal to actuator to open or close the valve. Now, imagine if you can create a membrane which has the signaling molecules inside, which can change their conformation upon the presence of some toxic species, and then if they, so that they can, once that they feel the presence of those unwanted chemicals, they can open or close the pores. So in this case, the membrane itself would act as a sensor, as a computer, as an actuator. So you actually remove the need of all those components. So you have a smart material which can make those decisions by themselves. So and that's the kind of work which that's the kind of materials we would like to create. We came to this idea first by observing many heterostructures, one of those heterostructures which exhibit multiple phase transitions and rapid changing in the properties, and we sort of derived the basic ideas. How do we create those materials? So I should say that these days we work on not only on 2D materials, a lot on 2D, but lots on organics, on polyelectrolytes, especially for membranes, MOFs and COFs for filtration, for in-membrane catalysis, but many others. But the basic principles is that you need to create a complex materials with a lot of components all together, and those components need to interact through multiple channels like van der Waals, strain, elastic fields, or Coulomb interaction, and so on. And then you can create the systems in the so-called metastable glassy state with multiple energy levels competing, so they can switch from one state to another, changing radically their properties and then responding to the changes in the immediate environment. So the whole structure looks very much like proteins in our body. So proteins are so versatile; they can do so many functions because they can conform into different folding, into different conformations, and then each of those conformations correspond to a particular functionality. And of course, so that's exactly what we would like to do with the inorganic, with our material systems. And of course, it's a very, very tough problem. So some of you might know that. So it's the problem of the protein folding is extremely complex. So AlphaFold managed to solve this one, the ground state, a few years ago. What we want to do is to learn all of the others and learn the rules for the transitions in between for our artificial crystals. Now it's it's pretty much an impossible task for physics. So of course we are all proud with the development of the physical sciences, in fact, but it's very, very naive still. We don't have any tools to talk about the metastable states, the out of equilibrium states, because once you want the active material, it needs to store energy somewhere. Upon signaling, release this energy, do something useful, just fold back and store the energy somewhere again. So it's a very out of equilibrium phenomena. We don't know how to describe them, so we try to use a lot of AI these days in our work, and we try to do quite some robotics, because you really need to generate a lot of data on those new materials, on the dynamic materials, to feed into your AI. So usually when I say robotics, people think about something like this. So that's we do have those as well. So our colleagues filmed our students and then just replicated everything in robots. So I should say it's much better to work with the students. You can't shout on a robot, right? So it's useless. But we do play with those, but in reality, it's a bit clumsy and slow. And so the majority of our robotic systems are very, very dedicated. So they just do a few steps, some simple material, but many times. So just really to generate a lot of data. And in the interest of time, I will probably skip the story on the artificial intelligence. I just say that in my institute now we have a good third of the efforts towards the applications of AI for the material science in many different directions. So this is just an example of how we derive how AI can learn physics and how AI can replace a scientist actually to make physical discoveries and learn the dynamic behavior of a complex material science system. In this case, it's a stretching of a polymer chain. But again, sorry, I won't stop here. But you can see that I'm very excited about this topic now. So we work a lot. But the sort of applications, the sort of materials we're trying to apply to are those dynamic, active materials which can do some interesting functionality. So this is the closest we got to the Terminator 2. Is the self-healing material. It's the high entropy alloy. So what you see here, so those is the TM picture. Those little dots are individual atoms, and then we just drill a hole in the middle. And then if you leave it for some time, and then give it a bit of time and some energy, it will completely self-heal and then just close this hole altogether. So it's in the right conditions, it takes a few minutes to completely seal this hole entirely. The problem is it's high entropy alloy. It's 7 metals plus oxygen there. So if you try to model it with any of the traditional ways how we model materials, either molecular dynamics or DFT, you would fail miserably. Absolutely no chance. So we are trying to work with apply AI to understand the dynamics. I mean, we understand the basic science, but then you take 20 different alloys, five of them work, 15 don't, and we really have no clue why. So we really need the help of AI here. Another example is on drug delivery. So we all had to take a vaccine against COVID-19, and we took a jab. And the reason for that is that mRNA vaccines, they're not very stable in the low pH of your stomach. So you will have to stick it directly into the bloodstream. Ideally, what you want a capsule which would be closed in the low pH of your stomach, open up in your intestine, releasing those drug molecules. So we need a signaling system in your nanocapsule to open or close. It's not that difficult. So you don't actually even need. So it's a very simple, just 3 different interactions. So you don't need to think much about AI even. So you can derive it from the first principles. And we have now this system being tested in mice, and so it looks like it works. I cannot show you a video of those. Those are, of course, tiny nanometer size nanocapsules, but exactly the same principles then can be applied for macroscopic motion, and then we can make those membranes sensitive to pH, light, temperature, humidity, anything. So you can trigger and make them move, make them make them active depending on any external signaling. So exactly the same principle can be used for the active anti-corrosion. So you create nanocapsules with some buffer solution inside, and you program them in such a way that so the protons are released upon the signaling from the low pH outside. So it's a new type of the active anti-corrosion coating. And maybe last example I wanted to give you. It's not really a material, but it's a complex dynamic system which we also play a lot with. It's the biological fuel cells. There are those bacteria which can emit electron during their life cycle, and then if you can combine, if you can collect those electrons, you can use it in the external circuit. So you basically have biological battery. And the beauty here that you start with monomers of a conductive polymer and a few bacteria, and those bacteria help those monomers to turn into conductive polymers. And then the more conductivity channels you've got, the more you promote the growth of the bacteria. They divide, so that your current get higher and higher and higher. And it's literally it's a self-growing battery system. You just feed it sugar, and then it just grows and give you electricity back. I should say that in our case we play with the polymers because it's a dynamic system, so it's highly nonlinear system, which is interesting to study with the artificial intelligence models, but with graphene it works like million times better. So the commercial ones we actually use graphene sponge, and it works really impressively well. Okay, I will stop here. Just say that it was a fantastic journey from graphene to 2D materials, and then artificial van der Waals heterostructures, but I think it really put a very good stepping stone to work on the dynamic and active materials, and that's exactly what we do now. I would really like to say thank you to many of my colleagues, also in Manchester, but also in Singapore. And just if you guys ever interested to learn more about our institute and about the AI for applications in materials, please visit. You can just visit us, or we have a conference next year, which is the first conference on the AI for science, and material science will be a big chunk of it. Thank you so much. It's really a pleasure. Thank you.
Thank you very much, Kostya, for a very insightful talk there. We've probably got a few minutes. Is there any questions, I guess? Apart from liquid robots, our liquid robot laboratories plan to open in 10 years' time. Kostya has just set as a new challenge. But any questions based on what you've just heard? Well, sorry, I missed that.
Yeah. Okay. Yeah. So.
They're changing the hybridization. So what's the advantage of the music?
To be honest, when we were doing the fluorographene, we were very excited. We thought about it as a two-dimensional analogy of Teflon, and it's fairly straightforward to produce, and it's reasonably stable. And unlike graphene, when you put hydrogen on top of graphene, when you put fluorine on top of graphene, it's actually rather stable. For some reason, it didn't get into many applications that I haven't seen. So I mean, we did this work a long time ago, but then it just stopped. So it was quite simple technology. I can't remember if we patented it or not, and I don't know. It's not there. So it's transparent. So it's all the same as boron nitride probably. So it's transparent. So it's a large band gap. So insulating. So boron nitride is being used for many different applications. Probably the biggest application of boron nitride is for memristor circuits now. So and for the membranes. Why fluorographene didn't go into that? I really don't know.
This one more question. Thank you very much. It's sound like the first question that maybe back then Latino was before the Latino's vaccines. And away from all the every side one against the but
Yeah.
it's just not the product.
I mean, vaccines have got its advantages. I would say probably the biggest advantage is that it's the ease of production, not the cost though, but the ease. So it's a fairly well developed technology. But look, I don't think there is a question of either or. So I work with some of the companies who produce carbon nanotubes, and we work quite nicely together. And if you look at modern batteries, so it's the recipe is so complex. It's carbon black, carbon nanotubes, graphene, nanosilicon, graphite. It's all together there. So it's like, so now it's each component is maybe 10%, 15%. So I won't be surprised if they will start adding vaccines there as well. For me, it's not a question of either or. So it's a question of finding the right material or the right combination for a particular application.
Yeah. Cool. Hey, go for you.
Well, I mean, so we mainly do it in the lab, and you can imagine guys, poor students, do it literally by hand. So that they take monolayer and then monolayer. So that's so far it's a bit, for us it's a bit childish from the point of view of industry. But at the same time, I should say, 20 years ago, when people started to talk about the applications of graphene, so they were asking us, I said, no, come on, what kind of applications? We just do it by Scotch tape. Within a few years, they managed to grow square kilometers of that. So I should say, so those heterostructures, some simplified ones, are actually being made by self-assembly. So actually, so for our dynamic systems, we do a lot of self-assembly. So we know how to charge them, and then we just add one on top of another. Then printing layers is also possible, and there are those applications, especially in the textile. So for the super cups, we just print several layers on top of each other, and there are efforts in growing those by CVD. So you need to know the sequence exactly, because you would create some diffusion processes, but it is doable. So there are efforts on the large scale production of those.
Okay, we'll take one more question.
Do you think that talking of that? Yeah.
From blood, not from mine. So guys, just if you're
Actually,
no.
We're looking for volunteers.
Yeah, I don't have that much blood. Sorry, guys.
In more to Kostya, as ever, thank you.
Thank you.
Excellent talk. Thank you. Yeah.